Curriculum. This course is divided into 3 chapters. Chapter 1 delves into the architecture of computers. Chapter 2 delves into the world of programming languages. To test our abilities, we'll be programming a rock, paper, scissors game at the end of this chapter. What is computer science? Contrary to popular belief, computer science does not limit itself to the study of computers. So what is it? According to Wikipedia, computer science is the study of the theory, experimentation, and engineering that form the basics for the design and use of computers. It is the scientific and practical approach to computation. Oh my, we're off to a very bad start. Let's opt for a more comprehensible and general definition. Computer science is a field which optimizes information systems. Computational optimization has been successfully applied to DNA sequencing and the solving of complex mathematical problems such as the Cadison-Singer problem, a question about the foundations of quantum physics that had remained unsolved for an astonishing 50 years. Computer science, in a nutshell, is really about solving as many problems from as many fields as possible. In computer science, information is data, which is processed, stored, or transmitted by a computer. Once this data is processed by the computer, it can generate useful output. What is optimization? In computer science, optimization is the process of modifying a system to make some of its features work more efficiently. To make a system more efficient, we use algorithms, a method to improve processes of all kinds. As the years go by, computational complexity increases. Information scientists and technologists make their lives a whole lot easier by retaining the useful and dismissing the useless. Now that you have a mild understanding of what computer science is and does, I will introduce you to the architecture of a standard computer. Well, there are bits, 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 and even more bits. And what the hell are bits? A bit is a physical object that has a size and location in space. The magic about bits is that they can be in one of 2 possible states at any given time. They might also change back and forth between these 2 states. If there is no electricity at a bit's location, then it's off. If electricity is present, you guessed it right, it's on. Logic gates. Logic gates perform a logical operation. Every logic gate either has a value of 1 or 0. Most logic gates have 2 binary inputs and 1 binary output. To make life a bit easier, picture 2 arrows flying into the front gate of a labyrinth and only one escaping. And implies continuation, or implies alternative, and not implies negation. Let's inspect all 3 of them. The AND gate is a logical conjunction, meaning that the mathematical expression A and B is true and only true when A is true and B is true. The upside down V is the so-called truth functional operator. As a visual aid, I suggest taking a look at this Venn diagram. It shows that the X and Y circles rely on each other. The OR gate is a logical disjunction, meaning that the mathematical expression A or B is true when A is true, or if B is true, or if both A and B are true. The V is the so-called truth functional operator. Once again, the Venn diagram helps us visualize this mathematical relationship. It shows that neither the X or Y circle depend on each other. The NOT gate is a logical negation, or simply called negation. Defining negation is tricky, somewhat ambiguous. Try to remember its mathematical/logical representation, which is not P. The Venn diagram depicts an empty circle. Software is a set of instructions which dictate the flow of electrical impulses within a computer. There are 2 main types of softwares. The first type is systems software. Examples include Android, an operating system used for mobile devices manufactured by Google, and iOS, an operating system used for mobile devices manufactured by Apple. The second type is applications software. Examples include WhatsApp, a free and cross-platform messaging and voice-over IP service, and iTunes, a media player, media library, and mobile device management application developed by Apple, everyone's favorite company. Hardware, contrary to a piece of software, is physical. It is directed by the piece of software to execute commands or instructions. Examples of hardware include the CPU, otherwise called the Central Processing Unit, RAM, also called Random Access Memory, and input devices such as a mouse or a keyboard. A piece of software performs some tasks on a computer. It changes the state of the computer hardware in a particular sequence. It tells hardware what to do, and it's malleable, which means that if I'm not content with my current piece of software, I can always add some new code to make it less buggy, more efficient, etc. Hardware is immalleable. A CD-ROM, display monitor, or printer are further examples of computer hardware. Last but not least, it is physically connected to a computer. This representation depicts a computer's most fundamental parts. The central processing unit contains the control unit, the ALU, also called the algorithmic logic unit, and the registers. Next to it, we have the random access memory, also called the main memory. Beneath it, we have the secondary memory. The wall which encompasses the CPU, the main and secondary memory, is called the bus, B-U-S, bus. It's a communication system which transfers data between components inside a computer. Next to the bus, we have input devices such as a keyboard or a mouse. These are only some of the output devices which give us a glimpse into what a computer is capable of producing and processing. The CPU is often referred to as the brain of the computer since it executes programs. So remember this, a CPU is to a computer what a brain is to a human body. Mobile phones, shiny Mac computers, even your grandpa's dusty and oversized television all possess a central processing unit. This is the motherboard, a platform which serves to connect important computer parts together, one of them being the central processing unit. On the motherboard, we also find RAM, Random Access Memory. How do the CPU and RAM interact? RAM consists of a collection of addresses. When a computer starts a program, the CPU sends an address to RAM to retrieve whatever information the program requires. This address, unlike any address you've ever seen, exclusively consists of ones and zeros, representing on and off wires. Once the enable wire is turned on, RAM sends whatever corresponding data it has back to the CPU. Finally, the CPU can start processing its information. The control unit is a circuit, which coordinates the activity of all other units in the computer system. Our diagram shows that the control unit tells the ALU, algorithmic logic unit, memory, as well as input and output devices how to respond to instructions received from a user. Algorithmic logic unit. Calculators calculate. Computers aren't any different. The algorithmic logic unit, ALU, is the basic element of a microprocessor. Its job is to carry out arithmetic operations such as subtraction, addition, multiplication, and division. At such a microscopic level, mathematical symbols such as division, subtraction, multiplication, and addition are represented by binary digits, ones and zeros. To see an ALU in action, let's take a good look at the following diagram. What you see here is what we call the machine cycle. We start off by retrieving instructions from the main memory, or random access memory. Then, the control unit decodes these instructions into a series of computer commands, making it possible for the ALU to execute. Then, the control unit decodes these instructions into a series of computer commands, making it possible for the ALU to execute these commands. Once the ALU has finished executing these commands, it sends the results back to the main memory. Registers, just like main and secondary memory, is a storage location. Let us take a look at the differences between a register and memory. A register holds the instructions that the CPU is currently processing. Memory holds instructions and the data that an executing program in the CPU requires. A register holds small amounts of data, typically around 32 to 64 bytes. Memory can hold anywhere from a couple gigabytes to several terabytes. To provide some perspective, 1 gigabyte is equivalent to 1,000 bytes, and 1 terabyte is equivalent to 1,000 gigabytes. And 1 terabyte is equivalent to 1,000 gigabytes. The CPU can operate on a register at a quicker rate than on a memory. The CPU accesses memory at a much slower rate than a register. Main memory versus secondary memory. We've seen the importance of main memory when discussing the interaction between it and the CPU. How does secondary memory compare to its bigger brother? Random access memory is also known as main memory. Secondary memory is also known as back memory. Main memory is categorized as volatile. Why? Because it doesn't store information for very long, since its intention is to quickly retrieve and dispose information. Secondary memory is categorized as non-volatile. Why? Because it stores information for a much longer period than RAM. Main memory is effective and fast enough to interact with microprocessors. Secondary memory is slow in interacting with the microprocessor. Main memory devices are connected to the computer through slots. Secondary memory devices are connected to the computer through cables.